this next hour is going to be all U.S. Geological Survey talks, and it's going to be on modeling of the watershed in the Clear Lake watershed. And first thing you might want to ask is, why are there 3 different models being used? And to answer that, we can go back to the 90s. USGS was tasked at that time with doing national water quality assessments. All right, and Congress was giving us something like $50 or $60 million a year every year to do this. And just like the Clear Lake watershed, like we saw on Charlie's map, there were dots in different watersheds, all right, from coast to coast, border to border. And our managers in Virginia said, well, you're telling us a lot of good information at these dots, but we have to know what's going on in the entire watershed, even if you can't monitor the entire watershed. So we got together statisticians, biogeochemists, and hydrologists to develop models, all right? And one of the first models that they developed was called the Sparrow model, and it worked great for these really large watersheds. So like in the Mississippi River, we saw like hotspots in Indiana where there were tile drains that were actually contributing to anoxia in the Gulf of Mexico, and similar things in Chesapeake Bay. So that was one modeling approach that Dina will talk about, but we didn't know how well that would work in a smaller watershed like Clear Lake. So we thought we need a plan B or a plan C. And so there's another model called hydrologic simulation program that Michelle will be talking about here in a minute. And that will also give us more information about the watershed. And then there was a relatively new approach that Charlie will be talking about called sediment fingerprinting, where you're going to use very detailed chemical markers to look at sediment in the watershed, in soils and whatnot, and see if you could trace those down to the lakes. That's why we have these 3 different modeling approaches. So with that, I'm going to hand the mic over to Michelle, and she'll talk about her approach.
Thanks, Joe. Can you hear me okay?
Yeah.
Okay, great. I'm going to pull in Alicia and hold the mic this time. Okay, so I'm Michelle Stern. I'm a hydrologist at the California Water Science Center in Sacramento. And yeah, thanks, Joe. We're going to be switching gears and talking a lot about modeling next. So I hope I don't lose everyone. It is the afternoon, so stay with me. My talk is called Watershed Modeling of the Clear Lake Tributaries. And before I get going, I'd just like to acknowledge all the funders of this work: CNRA, the Blue Ribbon Committee, and USGS, and the Bureau of Land Management. So I'll be talking about the overall problem statement, and then the project goals, the multi-model approach. And then I'll get into the model that I'll be really focused on, called Hydrological Simulation Program Fortran, or HSPF. And then I'll get into some results and summary of key findings. And this map on the right, this is kind of the model domain when I talk about the Clear Lake tributaries. Each one of these colored polygons is a main tributary that flows into Clear Lake. You can also see the stream gauges in the green triangles, and that yellow dot right here, this is the climate station that I'll be referring to later. So one of the main reasons we are all here gathered is to talk about harmful algal blooms, or HABs, and the mercury fish advisories in Clear Lake. It's a pretty major problem. And on the right, you can see a map from mywaterquality.california.gov. And this is a HAB advisory level map where people can report when they see HAB conditions. And so right now, this is as of August 7th. So a little over a week ago, you can see a lot of dangerous advisory levels around the lake. And actually, everything is either in warning or danger conditions or caution, except for a couple outliers. So process understanding is definitely needed to help determine the factors that cause HABs through time, importantly, and then how to mitigate those. One of the other problems is that previous work has relied on minimal data through time and spatially throughout the watershed. So the data collection that was described by Charlie Alpers, we've done a lot of data collection recently to kind of bolster the data available in the watershed to kind of understand what's going on better. but we still need more long-term data collection. And, that's kind of led to a limited understanding of the processes affecting HABs, although we've learned a lot recently. And we have limited to no data in the ungauged tributaries, which we'll see more of later. So the project goals for this task are to use a watershed model to better understand the hydrology and the relative contributions of stream flow, sediment, and nutrients to Clear Lake. And another goal of this task is to provide hourly inputs of stream flow, water temperature, sediment, and nutrients into Clear Lake. And then we're also linked up to the UC Davis Clear Lake hydrodynamic model that Alicia has been talking about and we'll talk more about tomorrow. And then another goal is to determine long-term trends of sediment and nutrient loads from each of the tributaries, including the ones that do not have long-term data. We can also try and understand how best management practices or BMPs may change sediment and nutrient loads through time. So when we talk about a multi-modeling approach, these are some of the models that are involved. But I want to back up and just talk about what is a model. Sergio talked a little bit about this in his talk. It's a mathematical representation of a process or relationship. And models are everywhere. They are, on your phone app when you look at the weather data, that's a model. Even our stream flow data that we call data is a model. I mean, it's built on a stage discharge relationship. And it's the gold standard of how we determine what discharge is, but that's also a model. So going forward, we're going to talk a lot about different types of models, and they all have different assumptions, and those assumptions can help you better understand how to use the data and then put them in context from other models. So on the left is kind of a diagram of what a watershed model tries to represent. You can see kind of the outside boundary of a watershed, and that's called a watershed basin. And HSPF is the hydrological simulation program for Fortran. I'll be calling it HSPF from now on because it's a very long name. So that's going to be the watershed model. And then we're also going to talk about LODEST. So Dina will be talking about that in her talk. And that is a statistical model that looks at its discharge to sediment or discharge to nutrients. And then Dina will also be talking about the Sparrow model that Joe introduced a little bit. It's a regression-based model that can help us determine where nutrients are coming from in the watershed. And then Charlie, in the next talk, will be talking about sediment fingerprinting, which is another statistical model that will try and determine where nutrients are coming from in the watershed. And then we have the hydrodynamic lake model that Alicia has been talking about and we'll kind of talk about more tomorrow. And we have some linkages between HSPF and Sparrow into this 3D lake model. So everything's kind of connected and working together. Okay, so hydrological simulation program Fortran or HSPF. This is on the left is kind of a diagram of the hydrological processes that it tries to represent. And it's a continuous deterministic lumped parameter modular model, which basically just means you can run a long simulation period. So we have an hourly model that runs from 1981 to present, just based on how long you have climate data for. And it's deterministic, meaning there's no random processes. It's not a probabilistic model. It's a lump parameter model, meaning every single one of the sub-watersheds has similar identical properties. And then modular, meaning we can run hydrology, and then we can run sediment transport and nutrients, and any combination of those. So HSPF simulates land surface and subsurface hydrology, stream and lake, simplified lake hydraulics, and water quality processes. And importantly, it was developed and backed by USGS and EPA since the 1960s, and accepted by the EPA for total maximum daily load or TMDL development. So telling you how much nutrients can you get into the system per day, right? And another important note is the weather data that's required to drive HSPF We need continuous hourly data. So that's including air temperature, precipitation, wind, solar radiation, and we're using the North American Land Data Assimilation System, or NLDAS dataset, more alphabet soup. And that was a dataset developed by NASA, and they have a lot of QA/QC procedures to make sure that it's a very good dataset, and it incorporates climate station data and radar data. Okay, so digging into some of the climate trends that we're seeing in Clear Lake. On the right, you can see an average maximum air temperature map, and this is a climatological average from 1981 to 2010. And these are kind of used by different agencies and researchers to look at long-term climate trends in an area. And with a map like this, you can see how much variation there is across the watershed, right? And if you're looking at one part of the watershed, what you're experiencing is not the same as what another person in a different part of the watershed is experiencing. So, in general, you're seeing cooler temperatures in the cooler colors. So that's kind of happening in the higher elevation parts of the watershed. And then when you get into kind of like the lake area and the surrounding towns, that's going to be a warmer area on average. And then if we look at this little dot, we pull out data from that one little dot, and we look at the annual time series for that dot from 1980 to 2023, we actually see a pretty clear increasing air temperature trend, which is probably not surprising to most of you, but it is a statistically significant trend, including, 2023 is kind of a low point, and even including that point, we have an increase in air temperature historically. If we do the same thing with precipitation, we can see that most of the precipitation falls in the upper parts of the watershed, right? Not in the lake area. The higher elevation areas tend to get more precipitation on average. And then, it's a lot drier in that lower and Oaks Arms area. What we can also see is a long-term decreasing trend in precipitation from 1980 to 2023. And that's including 2023, which is also a decent warmer year. So getting into some hydrology results, the calibration is actually done in steps because it's a modular model. So the first thing we do is calibrate hydrology and then move on to the sediment transport and the nutrients. And that is because one is heavily reliant on the other. Your sediment calibration relies on a good hydrology calibration. So to parameterize the model, I used gridded environmental data. So that's geology, land use, soils data, elevation data, and that creates kind of consistent parameters across all of the tributaries so that they're more directly comparable. And then we actually had a great data set from Sandra Bond and Jenny Curtis, who develops these vegetated and unvegetated ratios and road and trail density maps that actually help parameterize the sediment transport processes in Scotts Creek. We also incorporate geologic, atmospheric, and anthropogenic nutrient sources. And then we download the NWIS and DWR hourly stream flow gauge data for calibration. We also include measurements of sediment and nutrients. We're gathering all the data that we can historically from 1981 to present. And those are kind of, grab measurements and not always coinciding with stream flow data. And then we have Lodex daily estimates that will be kind of described more in Gina's talk. And those are great because it's actually a time series instead of just individual discrete data points. And the graph on the left, you can see precipitation on the top is a time series, and the graph below it is a hydrograph. Hydrologists like to put these up, and it kind of tells you a few things. You can see this is stream flow in cubic feet per second, and you can see how the peaks are, we're experiencing peak flow this is Kelsey Creek below Kelseyville, which has a really great long-term record of data. one of like 3 gauges that has long-term data, which is so valuable. So modeled data is in red and observed is in blue. And if you can't really see the difference, that means we're doing a good job. And, some peaks are oversimulated, some peaks are undersimulated. And you can see that more clearly in the scatter plot, where we have observed stream flow on one axis and modeled stream flow on the other. So you can actually see how we're lining up and the correlation there. Another thing we like to do is look at, the R squared and other statistical metrics to see how accurate we are. And this one has an R squared of 0.84. Okay, so with a calibrated hydrology model, I wanted to take a look at how, hydrodynamics in the watershed. And one of the big questions is in Scotts Creek, if you're familiar, we have Scotts Creek that flows down, and then we have this Scotts Creek at Eichhoff Road Bridge, and then it flows further down the watershed. It goes past the Blue Lakes, and then we get into Tule Lake, right? And then Tule Lake flows down, and then it meets with the Middle Creek in Clover Creek, and that flows into Clear Lake. And one of the main questions we wanted to ask is, how does the flow look below and above Tule Lake, right? So we have a gauge that's granted, a few miles up the watershed from Tule Lake, but we have above and below. So we're looking at this hydrograph here, and the top is precipitation again, and the bottom graph is all of the data that we've collected at both of these gauges. And this is just measured data. This isn't model data. And we can see that the red line is the Eichhoff Road Bridge. And so you can see the initial spikes in the hydrograph, and then they're quickly receding. But below Tule Lake, we're seeing in the blue line that the peaks are staying higher, and then they're receding much slower. We can also see the negative discharge, which is really cool and interesting about this gauge. We have negative discharge below Tule Lake, and that's not something that that HSBF can actually model. So we are a bit overestimating the flow in the model, but you can see that there is this shifted dynamic, right? There's lower peaks sometimes, and then there's longer duration of higher flows below Tule Lake. And then showing a very similar graph, but this is model data in red dashed line with the measured data in a blue line underneath. And so you can see we do not go into the negative values here, but in general, we are representing the system pretty well. We are showing we are like over and underestimating some peaks, but it's not a bias to just one direction. So the R squared here is 0.84, which means we're pretty much representing the system pretty accurately. And yeah, more data would be fantastic here so that we could actually see, what's happening in a very dry year, what's happening in an insanely wet year. These are both kind of like, I don't want to say average, but pretty average years. And then looking at water temperature, which has a lot of impact to the fish and wildlife and nutrient dynamics. So the water temperature here is at the same gauge below Tule Lake. And we can see that as the temperature is increasing into the summer, we're seeing that we're matching that dynamic. The measured data is in blue, the modeled is in orange, and then those sensors are ripped out in the summer, and that's why there's that gap. But you can see we're matching that data pretty well at this location. And then suspended sediment concentrations. So this is some of the challenges that we're running into with calibrating against the individual data points that are collected. You can see the measured data are the blue triangles, and the model data is the orange time series. And this is kind of an intermediate calibration, but you can see that it's just a challenge without a long-term record. And so the LOTUS data is really important because it kind of bridges the gaps between the time frame. So you can have a longer record and more data points. So one other result that we can do with this model is look at the relative contributions of stream flow into Clear Lake. And you can see that all of these basins are colored the same as that box plot. Thank you, Charlie, for explaining box plots, so I don't have to. Scotts Creek is all the way on the left in the box plot, and you can see that it's, it's like 30% of the area of all the tributaries. And so it makes sense that it contributes a lot of the stream flow. But what was surprising to me was that given any given year, Scotts Creek is not always it's not the same percentage contribution. So you can see on this bottom graph, the maximum contribution in gray, the average in blue, and the orange is the minimum. So you can see there's quite a bit of range of the percent contribution given any given water year. And so this has consequences for nutrient and sediment transport as well. Okay, so summary of the key findings. From 1981 to 2023, we see the average annual precipitation has decreased and average air temperature has increased. The hydrologic calibration results showed a pretty good representation of the system and the response to precipitation. Water temperature results also produced reasonable values. And the sediment transport and nutrient calibrations are ongoing and will simulate continuous hourly sediment and nutrient loads into Clear Lake. And I will pause and go back because this model will allow us to pull a time series for any one of these really small basins. So we not only have a time series at the outlet of each tributary, but we can also break it into any part in the watershed. And then going over the contributions, the largest ones are probably not surprising: Scotts Creek, 33 to 64%, Middle Creek, 14 to 27%, and Kelsey Creek, 7 to 27%. And it does widely vary depending on what year. And then the model comparisons will evaluate the different approaches and results, and that will allow us to get a better idea of what's going on in the watershed, what are the contributions to Clear Lake, and how complex of a model do you need to help answer some of these questions? So, one more slide. Please ask me any questions. Feel free to email me if we don't have time, but I want to acknowledge and thank everyone who's helped me with this work and all the conversations that I've had about hydrology so far, and I hope to continue all those conversations.
We got time for at least one question. Go ahead, Mike.
I'm interested to know what negative discharge is.
Goes backwards. The negative discharge, we have a velocity meter that Charlie was mentioning in an earlier talk, and they actually measure the flow going backwards into Tule Lake. And you can see it, yeah, it's a little back. But I think the net flow is going to be positive to where Clear Lake is.
I really want to see it. Look at our bathing stations in the building.
Yeah, but that's kind of, right?
Well, it's kind of, but it's still negative.
Yeah.
That's what the problem with these.
Oh.
So why we,
Go ahead.
So your model is pretty well calibrated to what's happening in real life. So what does that mean about using the model for managed incentives?
That's a great question. So what does having this model mean for management in the future? We plan to run climate change scenarios to look at the sensitivity of how how stream flow and nutrients will change in the future, just given changes in climate. And then we can also run changes in land use scenarios and best management practices to help managers decide how to manage the watershed. And hopefully, all of this calibration is really just providing confidence in the model results, and so that we can believe any scenarios that we do impose.